So I mentioned in an earlier video that there are many exceptions to the octet rule. And so we're going to go over some of the most common ones right here. One of the most common exceptions to the octet rule is the expanded octet. And this is the case where the central atom has more than 8 electrons around it. This can happen whenever you're dealing with an element in the third period or higher. And the reason is because these electrons, these extra electrons, can then go into d orbitals. So if you're in the third period, you can go into 3 d orbitals. And so in this case is BRF5. Bromine is in the fourth period, and so this is allowed. And you can see here, you have 42 valence electrons. All of these atoms are halogens, both bromine and fluorine. And so you have 6 atoms, 6 times 7, because 7 valence electrons for halogens. 6 times 7 is 42, so 42 valence electrons. You put bromine at the center because bromine is the least electronegative, fluorine is the most electronegative. Bromine's less electronegative than fluorine. And you basically put 8 electrons on fluorine, 2, 4, 6, and then the 2 share the bond. And you have 5 of those, 1, 2, 3, 4, 5. So that gives you 40. And then at this point, you have still 41st and the 42nd electron you have to put somewhere. Where do you put them? We put them on the central atom, which is bromine. Bromine here, so if all the fluorines are in congruence with the octet rule, 2, 4, 6, 8 electrons, but the bromine's not. It's wildly violating it. 2, 4, 6, 8, 10, and then the lone pair makes it up to 12. So that's definitely not the octet rule, but because bromine is in the fourth period, it's a higher than the third period, you can get this situation. All right, so what's next? Next is, again, some other looking at, what structures are best. And so we can go here and just like we did in the last video, look at formal charges. I trust that you can calculate these now using what we went over. These all have 32 valence electrons. This is for sulfate. Notice the trick that I told you, that all the formal charges have to equal to the charge of the ion. Sulfate's a 2- ion. So if you add this up, -1 plus -1 plus -1 plus -1 plus 2, that is -2, right? 0 plus 0 plus 0 plus -1 plus -1, that's equal to -2. 0 plus +1 plus -1 plus -1 plus -1, that's also equal to -2. So those are all correct assignments. And which one's going to be the best? Well, it's going to be this one. And why is that? That is because this has the most zeros. It has 3 zeros and only 2 non-zeros. This one has only 1 0, and this one has 0 zeros. So this is going to be your best structure. But that is a little weird. Why is that a little weird? Because this structure is actually violating the octet rule. Okay, and so this structure is definitely out because it's very high numbers. But this one is less out, I guess, but it's also violating the octet rule, right? Because sulfur is 2, 4, 6, 8, 10, and this sulfur is 2, 4, 6, 8, 10, 12. But because it's in the third row, this is actually a better reflection of the Lewis structure of sulfate versus this, just due to formal charges. What this is effectively telling you is that there wants to be, sulfur is able to violate the octet rule and get a little bit more electron density on sulfur to minimize, to distribute the charges better on the whole molecule. Another exception are molecules with odd number of valence electrons. If you have odd number of valence electrons, these are called free radicals. These will have 1 unpaired electron, and you just can't satisfy the octet rule. So you can think about NO2. That's going to be 5 for nitrogen and 12 for both of the oxygens. Oxygens with 6, so 12 plus 5 is 17. And these are some structures that you could draw, but somewhere you're going to have to put an unpaired electron, right? And you can use the formal charge business to figure out which one is best. These are equivalent structures. It's just we switched the double bonded oxygen. This one, it's on the right, and this one, it's on the left. Now, what does this mean if you have 2 equivalent resonance structures that are equally likely? That means that the reality is that you had a single bond in this structure, and you had a double bond in this structure, the reality is this is a 1.5 bond, and this is also a 1.5 bond. It's going to have intermediate bond strength between a single bond and bond length between a single bond and a double bond. All right, so here are some examples. Let's go through those. So this is for PF5. So let's look at these. Oops. Okay, so PF5, phosphorus is in group 5, so valence electrons 5 plus a halogen 7 for fluorine times there's 5 of them, so that's going to be 40. So we're going to figure out, phosphorus is a central atom because it's the least electronegative. But now we're going to have, and I'm not going to worry about our geometry here. We'll talk about the geometry when we get into VSPR again in a bit. But we're going to have 5 central atoms. I'm going to have the octet rule be satisfied for all of these. And that means that each of these fluorines has 2, 4, 6, 8 valence electrons. So that's all good. We have 40 electrons on the board. We're all good. The problem is, it's not really a problem, but it's a violation of the octet rule. Phosphorus is 4 step 2, 4, 6, 8, 10 valence electrons. That violates the octet rule, but because phosphorus is in the third period, this is the stable structure and how it exists. Now, because of this, basically those 2 extra electrons are going into the 3d orbitals. Now, if you're to consider NF5, this molecule can't exist, okay? Because that would be this, and nitrogen is in the second period. It doesn't have easy access to low-lying d orbitals, so it can't exist. Let's do boron trichloride here, valence electrides. Boron is in group 3, chlorine is a halogen, and there's 3 of them. So 3 plus 21 is 24 valence electrons. Write that out here. Boron is going to be the central atom. It's the least electronegative. Let's get the octet rule for chlorine by putting in 3 lone pairs, and 2, 4, 6, 8, and all the chlorines are equivalent. So 8 times 3, 24. We're good. But no octet rule satisfied. This is common occurrence for boron. Boron oftentimes will be an electron deficient molecule. And so it will have less than 8, a lot of times it'll have 6 valence electrons. Beryllium, it's not that boron can't have 8, sometimes it will have 8, and that's more stable, but a lot of times boron will only have 6. Beryllium, Be, will a lot of times only have 4 valence electrons. So these are just exceptions to the octet rule.